Hello everyone, I Goel, Assistant Professor in the Department of Electronics and Communication Engineering, AKGEC Engineering College. Welcome all of you in the video lecture of Communication Engineering. In the last video lecture, we have discussed about the modulation process that we used to perform in communication system at the transmitting side. We have seen the different types of modulation. We have understand what is modulation, what is the need of modulation, and how we can perform modulation at the transmitting sites. What are the various ways in which we can perform modulation? So the very first category of modulation is amplitude modulation. We have seen that under amplitude modulation we have various forms of amplitude modulations. They are double side bandwidth carrier or the conventional AM amplitude modulation, that is AM, double sideband with suppressed carrier, single sideband suppressed carrier, and vestigial sideband modulation. So today we are going to discuss about the conventional amplitude modulation, that is double sideband full carrier modulation. In double sideband full carrier modulation, that is the kind of amplitude modulation, the amplitude of the message signal is required to be impressed on the amplitude of the carrier signal. We can represent message signal and carrier signal with the help of this mathematical expression where mt is equals to am cos omega mt. Omega m we can mention in terms of frequency, that is omega m is equals to 2 pi f t. AM is the peak or the maximum amplitude of the message signal. Omega m is the angular frequency of the modulating signal. FM is the modulating signal frequency. Similarly, we can represent carrier signal, that is a high frequency periodic waveform, mathematically as CT equals to AC cos omega CT or CT equals to AC cos 2 pi FCT, where AC is the carrier or the maximum amplitude of the carrier signal. Omega m is the angular frequency of the carrier signal in radians per second, and Fc is the carrier frequency in hertz. So let us understand how we can impress the amplitude of the message signal on the amplitude of the carrier signal. The standard equation of amplitude modulation can be expressed with the help of this mathematical expression where St equals to AC 1 plus Ka mt cos 2 pi Fct. In this mathematical expression, AC is the amplitude of the carrier signal, Ka is a constant which is the amplitude sensitivity parameter of the modulator, mt is the message signal, and Fc is the frequency of the carrier signal. In this expression, substituting the value of mt, that is the message signal, as am cos omega mt, we will get St equals to AC 1 plus k into am cos 2 pi fmt. We have replaced omega m with 2 pi fm into cos 2 pi fct. If we will take the product of these two terms, that is Ka into am, this will turn into mu, which is called as modulation index or the modulation factor. So we can represent this expression as St equals to AC 1 plus mu cos 2 pi fmt into cos 2 pi fct, where mu that is equals to K into am we have defined as a modulation index or modulation factor. Single tone AM modulation. What is single tone AM modulation? If we are considering only one message signal, then it is called as single tone amplitude modulation. So we have considered mt is equals to cos 2 pi fmt, am into cos 2 pi fmt. So in the last equation, how we can perform this amplitude modulation? What is amplitude modulation? In AM, the amplitude of the high frequency carrier signal vary according to the amplitude or the instantaneous value of the message signal. So, here in the amplitude modulated waveform, the amplitude of the carrier, that is this portion, now after modulation will become AC plus MT. The amplitude of the carrier after modulation will become AC plus MT, where MT is the message signal into cos omega CT. This portion AC plus MT, that is the amplitude of the modulated waveform, is also known as envelope of the carrier or envelope of the modulated waveform. So, in this expression, to obtain the single tone AM wave expression, we have put MT is equals to AM cos omega MT. In the next step, we are expanding this equation to obtain the expression for the modulated waveform. So, multiplying AC plus AM cos omega MT with cos omega CT, we will get the first term AC into cos omega CT plus 1 by 2 into 2 AM cos omega MT into cos omega CT. We have multiplied the second term with 2 and divide with 2 to convert this into a different expression. So, after multiplying the second term, after multiplying and dividing the second term with 2, we will get the AC cos omega CT plus AM by 2 cos A cos B. So, with the help of the trigonometric relationship of 2 cos A cos B, we can write down this expression as cos of omega C plus omega MT plus cos of omega C minus omega MT. After expanding the next line, we will get AC cos omega CT plus AM divided by 2 into AC divided by AC. We are multiplying and dividing the term with AC. So, we will get AM by 2 AC by AC cos of omega C plus omega MT cos of omega C minus omega MT. This portion, in the next line, we are rearranging this equation as AM by AC and we are separating the term AC by 2. This ratio of AM by AC is also called as modulation index or the modulation factor. So, we can define modulation index or modulation factor as the ratio of AM by AC, where AM is the maximum amplitude of the message signal and AC is the amplitude of the carrier signal. So, we will get finally that the modulated waveform in time domain can be represented as AC cos omega CT plus AC m by 2 cos of omega C plus omega MT plus AC m by 2 cos of omega C minus omega MT. So, we are getting 3 terms in the amplitude modulated waveform. Here we have obtained this expression for single tone AM modulation. Representing the same expression in terms of frequency f, we can write the above expression as AC dot cos 2 pi FCT plus AC m by 2 into cos of 2 pi FC plus FMT plus AC m by 2 cos of 2 pi FC minus FMT, where FC is the frequency of the carrier and FM is the frequency of the modulating signal or the message signal. The very first term in this modulated waveform expression is the indication of the carrier. The second term is the indication of the upper side band, where we are getting frequency little bit more than the frequency of the carrier, that is the summation of FC plus FM. The third term is used to be called as lower side band, that is LSB, where we are getting frequency lesser than the carrier frequency. So, in the amplitude modulated waveform, we have 3 terms. The first term indicates the carrier, the second term indicates the upper side band and the third term indicates lower side band. The amplitude of the carrier is AC. The amplitude of the upper sideband, that is the summation of frequency, carrier and modulating signal frequency. The amplitude of this upper sideband is AC m by 2, where m is the modulation index, and the lower sideband with the same amplitude, that is AC m by 2. We can represent this expression of the amplitude modulated waveform in frequency domain also. So, how we can represent this time domain expression in frequency domain expression, as we have discussed in the first few lectures, that we can perform two types of analysis of a signal, that is a time domain analysis and frequency domain analysis. If we want to perform the frequency domain analysis of a time domain signal, then we need to take Fourier transform of that particular signal. So, after taking the Fourier transform of the above expression, that is the expression of amplitude modulated waveform, we will get this expression, which is equal to S of f, that is the Fourier transform of S of t is equals to 1 by 2 AC del of f minus fc plus del of f plus fc. Similarly, the Fourier transform of the second term will become 1 by 4 m AC del of f minus fc minus fm plus del of f plus fc plus fm. Similarly, we can have the Fourier transform of the third term equals to 1 by 4 m of AC del of f minus fc plus fm plus del of f plus fc minus fm. Now, we can draw the frequency spectrum of the above expression in this manner. Here, the horizontal axis represent the frequency. This axis will represent the Fourier transform, that is the amplitude of the each term. So, according to the above expression, how we can draw this frequency spectrum of the AM signal? First, we have the carrier signal at frequency fc. First, we are drawing for carrier signal. So, we have f minus fc del of f minus fc, when this particular delta function will exist when f is equals to fc. So, we have drawn a carrier at f is equals to fc. This particular portion will exist when f is equals to minus of fc. So, we have drawn here f is equals to minus fc, the value of the carrier. The amplitude of the carrier at this point is equals to AC by 2. So, here we have mentioned the amplitude of this function. The next, we are going to draw the upper sideband and the lower sideband. So, upper sideband containing frequency fc plus fm and minus of fc plus fm. Similarly, we can draw the spectrum for lower sideband having the frequency fc minus fm and minus of fc minus fm. The amplitude of upper sideband and lower sideband are same, which is m AC by 4. So, here we have mentioned the amplitude of lower sideband and upper sideband. So, this is the frequency domain representation or the spectrum representation of the amplitude modulated waveform. From this frequency spectrum, we can calculate the total bandwidth we required for the transmission of AM signal. Transmission bandwidth is the bandwidth that we can calculate by taking the difference between the frequencies of lower sideband and upper sideband. Transmission bandwidth is the total bandwidth required for the transmission of AM wave signal. So, how we can calculate what amount of bandwidth we require to transmit this particular signal amplitude modulated waveform? The transmission bandwidth can be calculated by taking the difference of upper sideband frequency and lower sideband frequency. The upper sideband frequency is the summation of carrier frequency and modulating signal frequency, that is fc plus fm. The lower sideband frequency is the difference of the carrier frequency and message signal frequency, that is Fc minus Fm. Taking the difference of both the terms, we will get the transmission bandwidth equals to twice of Fm. So, the total bandwidth required for the transmission of AM signal is twice the value of modulating frequency. In this amplitude modulated waveform expression, we have seen a term that is called modulation index. Let us understand what is modulation index or modulation factor. Modulation index is defined as a parameter which determines the amount or depth of modulation. For amplitude modulation, it can be defined as a measure of the extent which a carrier voltage or a carrier amplitude can be changed according to the modulating signal, that is message signal. So, what is modulation index? We can say it is a parameter that will tell us, or that is a measure of the extent that how much amplitude of the carrier signal can be varied according to the instantaneous value of the message signal. We can also define modulation index as the ratio of the peak amplitude of the message signal to the amplitude of the carrier signal. So, we can define modulation index as a ratio of AM upon AC, where AM is the peak amplitude of the message signal and AC is the peak amplitude of the carrier signal. We have also seen that we can define mu, that is modulation index, as a product of Ka. Ka is the amplitude sensitivity parameter into the maximum amplitude of the message signal. So, modulation index can also be defined as a product of Ka into Am. The next thing is percentage of modulation index. What is the percentage of modulation index? The percentage of modulation index we can calculate simply by multiplying the ratio of AM by AC into 100. We generally used to define the modulation index in terms of percentage. So, how we can calculate the percentage of modulation index? Just by multiplying the ratio of AM by AC into 100. The modulation index or modulation depth is also referred as percentage of modulation or the depth of modulation. So, by simply multiplying this ratio with 100, we can get the percentage modulation. Here we have shown a amplitude modulated waveform. This is the carrier signal. The amplitude of this carrier signal is varying according to the amplitude of the message signal. This outer line is called as envelope of the modulated waveform. This is the maximum amplitude of the modulated waveform. This is the minimum amplitude of the modulated waveform. The maximum amplitude can be equals to AC plus AM and the minimum amplitude can be equals to AC minus AM. So, we can also define modulation index, or we can calculate modulation index with the help of this expression, where it is equals to A max minus A minimum divided by A max plus A minimum, where A max is the maximum amplitude of the modulated waveform and A minimum is the minimum amplitude of the modulated waveform. So, the modulation index or the modulation parameter can also be calculated with the help of this expression. On the basis of this, we can have three conditions of modulation in amplitude modulation. These three conditions, or we can say the 3 degree or the 3 depth of the modulations, are under modulation, critical modulation and over modulation. What is under modulation? It is the case where we get the value of modulation index less than 1. Modulation index is a parameter which is generally defined between the range 0 to 1 or in percentage. So, if the value of this modulation index is coming out to be lesser than 1, then it is called as under modulated waveform. When we will get the value of modulation index is equals to 1, then it is used to be called as ideal modulation or perfect modulation or critical modulation. If we are getting the value of modulation index greater than 1, then it is called as over modulated waveform. Let us observe how these waveforms looks like. Here we have the first one is under modulated waveform. Modulation index, as we have discussed, is the ratio of AM upon AC. If the maximum amplitude of the message signal is lesser than the maximum amplitude of the carrier signal, then we will have this condition of under modulation. Here the maximum amplitude of the message signal is lesser than the maximum amplitude of the carrier signal. So, this minimum value is not reaching or coinciding with this axis. So, this is the case of under modulation. The second one is the critical modulation, where mu is equals to 1 or exactly 100%. When we will get this condition? When the maximum amplitude of the message signal is exactly equal to the maximum amplitude of the carrier signal. So, in this condition we will have mu equals to 1. The third condition, that is the case of over modulation, we will have this condition of over modulation when the maximum amplitude of the message signal to be greater than the maximum amplitude of the carrier signal. So, what happens in this case? When we have the maximum amplitude of the message signal greater than the maximum amplitude of the carrier signal, then a part of information, or we can say a part of a message signal, will not be transmitted properly, and we will have losses. We will have loss of the information, and it will cause distortion of the information or the signal, message signal. Here we will get other sidebands or the phase reversal of the carrier signal. So, in case of over modulation, we used to get distortion of the information. So, we have discussed what will be the expression of amplitude modulated waveform, and what are the three cases of modulation index in case of amplitude modulation. Now, let us calculate the power and efficiency of a amplitude modulated waveform. How we can calculate the power of AM wave signal? Considering the standard, considering the equation of the AM wave that we have just calculated, how we can calculate the power of this amplitude modulated waveform? We know that power we can calculate with the help of mathematical expression of this waveform, as this expression includes three different terms. So, the power of AM wave is equal to the sum of carrier power, lower sideband power, that is upper sideband power, and lower sideband frequency component power. So, by adding the power of these three terms, we can have the total power of amplitude modulated waveform. We know the standard formula for calculating the power of a cos signal. Three of these terms having the cos function. So, how we can calculate the power of a cos function? The power of a cos function can be calculated as V square RMS divided by R. What is V square RMS? That is the maximum value of Okay, so how we can calculate the power of a cos function? We know the standard formula for calculating the power of a cos function, that is V square RMS divided by R. So it will become RMS value of the voltage is equals to the maximum value of the voltage divided by root 2 whole square divided by R. So what is the voltage or the maximum value? That is equivalent to the amplitude of the cos function. So how we can calculate power of this amplitude modulated waveform? It is the summation of the power of the carrier signal and the power of the sidebands. So we can write the total power as a summation of power of the carrier signal and the power of the sidebands. Here we are having two sideband, upper sideband and lower sideband. So we can further express this equation as PT, that is the total power, equals to PC plus PUSB plus PLSB. Now individually we can calculate the carrier power, lower sideband power and upper sideband power. So first we are calculating the carrier power. The carrier power is equals to V max divided by root 2 whole square divided by R. In our expression, what is the value of V max? That is equivalent to AC, that is the amplitude of the carrier signal. So it will become AC divided by root 2 whole square divided by R. Simplifying this expression, we will get the carrier power equals to AC square divided by 2R. The next we can calculate the power of lower sideband and upper sideband in the similar manner. So by observing the equation, we can observe that the amplitude of lower sideband as well as upper sideband is same. So we will get the same power in lower sideband as well in upper sideband. So the power of LSB and USB is same, which is equal to the AC mu divided by 2 root 2 whole square. What is the amplitude of my upper sideband and lower sideband? That is AC mu by 2. So replacing V max with AC mu by 2, in the expression we will get the power of lower sideband and the power of upper sideband equals to AC square mu square divided by 8R. Okay. So this will become the carrier power and this will become the power of the sideband. Now putting the two values, that is the power of carrier and power of upper sideband and power of lower sideband in the total power expression, we will get PT equals to AC square by 2R, that is the power of carrier, power of lower sideband and power of upper sideband. Adding these three terms and taking AC square by 2R common, we will get the total power required for transmitting amplitude modulated waveform equals to PC 1 plus mu square by 2. So this is the total power required for transmitting an amplitude modulated waveform. Okay. So this is the expression for the power required for the transmission of AM wave. Here we can note down one point, that when we are transmitting amplitude modulated waveform, we are having three contents or we are having three parts in our waveform, that is carrier, upper sideband and lower sideband. Okay. But in AM signal waveform, the carrier does not contain any information about the signal. The useful signal the useful information will be contained by the lower sideband and in upper sideband, that is the sidebands. Carrier does not contain any information of the message signal. So the power required for transmitting the carrier is a wastage for us, but we have to transmit the carrier also because of its easier detection and transmission. Next, what we can calculate, this we have calculated the total power required for the transmission of AM wave. Now we can calculate the efficiency, what amount of efficiency we are getting with the help of this double sideband full carrier modulation. What is efficiency? Efficiency we can define as the ratio of sideband power to the total power required for the transmission of AM signal. The amount of useful masses power present in AM wave is expressed in terms of transmission efficiency. That means efficiency will tell us the amount of useful information we are transmitting. Okay, it can be defined as a ratio of power in the sidebands to the total power. How we can represent efficiency? As a ratio of sideband power to the total power required for the transmission of AM wave. Efficiency we can define as a ratio of sideband power to the total power. Why? Because the useful information is contained only in the sidebands. Carrier does not contain any useful information about the masses signal. So, sideband includes in AM wave as lower sideband and upper sideband. The total power includes carrier also. So, by putting the value of PLSB, PUSB and P total from the previous expression that we have obtained for the power of carrier, lower sideband and upper sideband, we will get efficiency is equals to MA square PC divided by 2 divided by PC1 plus MA square by 2. To calculate this efficiency into percentage, we have multiplied this term with 100. So, what expression we will get for the efficiency as a ratio of M square divided by 2 plus M square. What is this? MA, it is modulation index. So, we can simply write down that efficiency as a ratio of mu square divided by 2 plus mu square. If we want to calculate this efficiency into percentage, we can simply multiply this term with 100 and will get the percentage efficiency as the ratio of power in sidebands divided by total power into 100. How we can calculate the maximum efficiency of AM wave? What maximum amount of efficiency we are getting? The maximum efficiency, that is the ratio of 2 plus mu square, where mu is the modulation index. The maximum value of modulation index we can have in amplitude modulation equals to 1. So, by putting this value in above expression, we will have percentage efficiency then become around 33.33%. So, this is the maximum efficiency we can have in double sideband full carrier amplitude modulation, that is 33.33%. This indicates that 2/3 of the power is wasted and only 1/3 of the total power is used for the transmission of masses signal, because we have to send carrier also, and so the power and carrier does not have any useful information about the masses signal. So, the power required for transmitting the carrier is a wastage for us in this particular kind of modulation. So, what we can do? We can minimize or we can eliminate the need of transmitting the carrier. That is our second type of amplitude modulation, double sideband with suppressed carrier. So, we can increase this efficiency, that we will discuss in our next video lecture.